Okay, so hello and welcome back. So in this list of videos, we are going to be talking about basically NCERT mathematics class 11 chapter 9, which is about sequences and series. So if you have already not done so, you can go back to class 10. I mean what you need to basically the prerequisite for this chapter is mainly basically class 10, chapter 5, I suppose. Class 10, chapter 5, which is about arithmetic progressions. Class 10, chapter 5, which is about arithmetic progressions, because we are going to talk a little bit about, we are going to use what we learned in this chapter and then build upon that and also introduce some new material based on what we learned over there. Of course, naturally you understand that you need to essentially know everything that comes before this chapter in these lines of books. That's always true in the case of anything that you do in mathematics, but and the book that you need for this specific number of videos in this playlist. Okay, so to get the book, basically you need to go to this address, ncert.nic.in/textbook/textbook.htm, and then you can go over here to class 11 mathematics, and if you hit go, then you will have the book over here, and then now you can download the complete book here, meaning all of the chapters of class 11. Now we are in this playlist, we are doing chapter 9, which is related to sequences and series, right? So that's what we are doing in this chapter, in this playlist, basically, right? You can of course download this specific chapter by clicking this button here, or you can download the complete book. But I suppose if you are already a student in India, then you already know all of these. These are relevant to those people who have come here and know nothing about NCERT and the whole system that goes on in India. So that's basically what we are doing right now. Okay. So as an introduction to sequences and series, so basically you can say that a sequence, basically when we say a sequence, we say that the collection of objects is listed in a sequence. When we say that when a collection of objects is basically listed in a sequence, and I'm saying this in the mathematical sense. Maybe in the English language, people sometimes choose to use the word in different contexts, having different meanings. But when in mathematics we say that a collection of objects is listed in a sequence, what that means is that the collection is ordered That means that the collection is ordered in such a way that it has an identified first member, second member, third member, and so on. So that the collection is ordered in such a way that it has an identified basically first member, second member, third member, and so on and so forth. Right? So for example, basically the population of human beings or bacteria at different times, at different points in time, if you basically assign some numbers to them and write down the numbers one after the other, that would be a sequence, right? Or the amount of money that you deposit in a bank account as a part of some investment or something, that is basically also, that forms a sequence. Or for example, the depreciated values of certain, for example, commodities that occur in that over a period of time, that's again a sequence. And so there are basically some sequences. There are some sequences that, and of course these are basically concepts that you need to understand. This is the vocabulary that you need to understand here. There are some sequences that follow basically following specific patterns. And these, if that is the case, for example, there are some sequences that follow specific patterns. These kinds of sequences are called progressions. Meaning that, for example, in the previous chapter in the class 10, chapter 5, we talked about the arithmetic progression. So in an arithmetic progression, you essentially have a list of numbers, or you have a collection of objects listed in a sequence. So you essentially, in an arithmetic progression, you essentially have a sequence of numbers that basically, for example, you have 1, 3, 5, 7, 9, and so on and so forth. So you can see that that these objects, they basically, this you can call a sequence that follows a specific pattern. And the specific pattern over here is that basically each of the numbers starting from the first object, you add 2 to the first object to get to the second object. Add 2 to the second object to get to the third object. Add 2 to the third object to get to the fourth object, and so on and so forth. That means that the difference between each two consecutive objects is exactly always 2. And that is the specific pattern that, for example, you can find over here. And that's, and for the same reason, meaning because of the fact that basically this sequence follows a specific pattern, it's called a progression. And in this case, it's called an arithmetic progression. Now we have, for example, other types of progressions. For example, we have geometric progressions. We have all types of different things, of course. But but here basically the important thing to understand is that a sequence is basically a sequence is basically a collection of objects that is ordered in such a way, a collection of objects that is ordered in such a way that it has an identified first element, second element, third element, and so on and so forth. If you have such a collection of objects, that is called a sequence, right? Now, if this sequence follows a specific pattern, then that sequence is called a progression, right? That's what you need to learn so far from this whole discussion. Now, in order to understand sequences, let's consider some examples here and see basically what we have here. Okay, so now let's first understand the idea of a sequence, and let's first understand the idea of a sequence, and then we will talk a little. We will basically move inside this chapter. Okay, so now let's consider the following examples. So assume that there is a generation gap of 30 years. Let's assume that there is a generation gap of 30 years. So what that means is that, the way that I understand this is that the generation that comes before you can essentially think of that as, I don't know. Anyway, you can actually, for example, you could imagine that on average, every 30 years there is one generation change in human beings, something like that. What that means is that now, for example, now if you are asked to find the number of ancestors, if you're asked to find the number of ancestors that a person had over the course of, for example, over the course of 300 years, right? Over the course of 300 years. If you're asked to do this, to find the number of ancestors that the person had over the course of 300 years. Now, over the course of 300 years, you have 300 years to basically 30 generation per, that's the number of generations per that's the number of years per generation, right? That's the number of years per generation, meaning that every 30 years you have one generation. So you have 300 years and you have 30 year per generation. That would give you basically 300 years. That would give you 300 divided by 30, year divided by basically year per generation, and that's the same thing as if you take the reciprocal of this, you would have basically 300 divided by 30 is equal to 10, and year, you have year times basically generation per year, and these two you can cancel out. You will be left with 10 10 generations. 10 generations. Which means that if there is a generation gap of 30 years, then 300 years would correspond to 10 generations. To 10 generations, right? Now, so that means that over the course of 300 years, this person whose number of ancestors here we wish to calculate, this person had actually 10, there were 10 generations before this person. So, or basically there were 10 generations within these 300 years basically. So now, in order to understand how to deal with this problem, you can essentially imagine that this is you as the person whose number of ancestors we want to calculate, and this person, of course, has a father, he has a mother, right? So this is one generation. This is in essentially one generation. This is one generation. Now this father and mother, had each of them, of course, had to have a father and a mother and a mother. So this has a father and mother. This has a father and a mother. And so this would be a father for the father, a mother for the mother, a father for the mother, a mother for the mother, and that would be another generation, right? Then again, this person over here, he had to have a father, he had to have a mother. This person over here, he had to have a father and a mother, a father and a mother, a father and a mother, right? So that means that you have a father over here, a mother over here, a father over here, a mother over here, a father, a mother, a father, a mother, and you can just keep going all the way up to 10 generations. Which means that basically over here, the number of ancestors that you have in this generation is 2. Then in this generation you had 4 ancestors. In this generation you had 2, 4, 6, 8 ancestors, and you can just keep going. Meaning that the number of ancestors that you had in the first generation was 2, in the second generation was 4, in the third generation was 8, and so on and so forth. Which means that basically in the 10th generation, so you can write this as basically 2 raised to the power 1. When your n is equal to 1, you can write this as 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3. Which means that in the 10th generation, you had 2 raised to the power 10 ancestors, right? This is the 10th generation. The 10th generation. And this is the first generation, right? So that's basically that. Now this is of course in the beginning of this chapter we talked about essentially 2 ideas. We talked about the idea of a sequence, and we talked about the idea of a progression. So we said that a sequence is basically a collection of objects in which basically there is a definite and identified first element, there is an identified second element, there is an identified third element, and so on and so forth. Or to be more exact, we said that basically when we say that a collection of objects is listed in a sequence, we usually mean that the collection is ordered in such a way that in such a way that it has an identified first element, second element, third element, and so on and so forth. So that was the idea of a sequence. Now we said that basically then if these sequences follow specific patterns, we call them progressions. And as an example of a progression, we gave the example of an arithmetic progression. Of course, you can see that these numbers that you can see over here, this is no arithmetic progression. This is basically called a geometric progression, because essentially what you can see here is that the first term, which is 2 over here, if you multiply the first term by 2, you will get 2 times 2, which is equal to 4. Multiply this term by 2, 4 times 2, you will get an 8, 2, 4, 8. Multiply this term by 2, you will get a 16. Multiply this term by 2, you will get a 32. You will get a 32. And of course, it basically follows the same pattern here, meaning that you can write this as 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, 2 raised to the power 4, and 2 raised to the power 5, and so on and so forth, and so on and so forth, right? So this is basically called the geometric progression. This is in mathematics called a geometric progression. But essentially we will find out more about this as we go along in this chapter, basically. Okay, so now in order to answer the question that we wanted to answer, that basically how many ancestors does this person have? Of course, then you know that now you know the number of terms for the term for the first generation, for the second generation, and so on and so forth. But then essentially we will have to find a way to find the sum of these terms. In the case of an arithmetic progression, we basically found some way. And we said that basically S of n was equal to n divided by 2 times basically 2a plus n minus 1 times d. We found this formula, and using this formula, basically we could calculate the sum of basically the first n terms of an arithmetic progression. This was for an arithmetic progression. But since this is no arithmetic progression, this is geometric progression, we will have to find some way in order to basically add all of these terms together. So then the number of the person's ancestors for the first, second, third, and so on and so forth, and all the way up to the 10th generation, would therefore be 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, all the way up to 2 raised to the power 10, basically people. And these numbers form what we call a sequence, right? So for now we can call them a sequence, and then since they follow a specific basically pattern, we can call it a progression, and then it's a specific type of a progression which is called a geometric progression. But then we will talk about all of these in the coming videos, right? Now, so as another example, we can consider the successive quotients that we obtain in the division of 10 by 3 at different steps of division. So when you divide 10 by 3, you will get, basically 3.33333 and repeating, right? So in the first step, you're going to get a 3. In the second step of division, meaning that you write basically 10 divided by 3, you will have 3 times 3 is equal to 9 and 1 remainder, so you got a 3 over here. Then if you add a decimal point over here and a 0 over here, you will have basically a 10 over here, so again you will get, I'm sorry, there is no 0 over there actually. You will have basically 3 times 3 again, which is 3 times is equal to 9, 1 remainder, 0, 0. So this is the second step, which you will get 3.3. In the third step, you add a 0, and then again 3 times 3 is equal to 9, 1 remainder. So you got 3.33, and so on and so forth. So as you can see, over here the number of decimal places is 0, the number of decimal places is 1, 2, and so on and so forth. So these quotients also form a sequence, and using these examples you can actually understand what we mean by a sequence. The various numbers occurring in a sequence are called the terms. These are the various numbers occurring in a sequence, which we call basically terms, the terms of the sequence, right? So the various numbers occurring in a sequence are called its terms. We denote the terms of a sequence by A1, A2, A3, all the way up to A of n. So the terms of the sequence are denoted by A1, A2, A3, and all the way up to A of n, and so on and so forth, right? These are the terms of the sequence. And the subscripts denote the position of the term, of course, right? And the nth term is the number at the nth position of the sequence and is denoted by A of n. So this is at the nth position of the sequence, it's called A of n. And the nth term is also called the general term of the sequence. This is called the general term. This is called the general term of the sequence. The general term of the sequence. Thus, the terms of the sequence of persons' ancestors mentioned above are, for example, so that you can say that the terms of the sequence of the person's ancestors is basically 2. A1 is equal to 2, and A of 2 is equal to 4, A of 3 is equal to 8, and so on and so forth. All the way up to A of 10, which is equal to 1024, 10 raised to the power 10, right? 2 raised to the power 10, I'm sorry. So similarly, in the example of the successive quotients, you can say that in the example of the successive quotients, we have basically what we found out was that basically A of 1 was equal to 3, and A of 2 was 3.3, and A of 3 was 3.33, and so on and so forth, all the way up to A of 6, which was, for example, you can write A of 6 is equal to 3.3333336 5 times, and etc. Right? So now as a definition, or something like a definition, you can say that the sequence containing a finite number of terms is called a finite sequence. So a finite sequence is basically a sequence with a finite number of terms. Right? So a sequence basically containing a finite number of terms is called a finite sequence. For example, the sequence of the ancestors of this person is a finite sequence because it contains 10 terms, a fixed number basically. And we also have the idea of an infinite sequence, infinite sequence, which is basically a sequence with an infinite number of terms. So a sequence is called infinite if it's not a finite sequence, or basically a sequence, you can say a sequence that is not finite. For whatever reason they have defined it this way and not this way. Probably this could have some other meaning, so I'm going to forget about my own definition, because you might say something and you might actually not know that what you say might actually mean something else. So I'm not going to. I just simply take that back and write an infinite sequence as a sequence that is not finite. Okay. So a sequence is called infinite if it's not a finite sequence. For example, the sequence of the successive quotients mentioned above here, that is an infinite sequence. Infinite in the sense that it actually never ends. It just keeps going and going and going, right? Now, often it's possible to express the rule which yields the various terms of a sequence in terms of algebraic formulae. Meaning that, for example, in the case of this sequence, I can say that a of n, in the case of this sequence, I can say that a of n is equal to 2 raised to the power n. For example, here, 2 raised to the power 1 is equal to 2, 2 raised to the power 2 is equal to 4, 2 raised to the power 3 is equal to 8, 2 raised to the power 10 is equal to 1024. And so the algebraic rule that you can find here is, for example, 2 raised to the power n. And therefore, basically, of course, that's helpful, and we can use it in many different ways. As an example, let's consider the example of, for example, basically the sequence of even natural numbers. Let's consider a sequence of even natural numbers. For example, which is of course 2, 4, 6, and 6, 8, and so on and so forth. So here your A1, or A of 1, I should say probably, is 2, which is equal to 2 times 1. 2 times 1. A of 2 is equal to 4, which is the same thing as 2 times 2. A of 3 is the same thing as 6, which is equal to 2 times 3. And A of 4 is the same thing as 8, which is equal to 2 times 4, which means that basically, so that the 2 remains the same, and so you can write it, you can also, I said that basically you can write it as 2 raised to the power n, but you can write it as basically, you can write it as 2 times n probably. Let's see how that goes. So what that means is that a of 4 is equal to 8, which is equal to 2 times 4. And a of 23 okay, 2, 4, oh, okay, that's a different thing. I'm sorry. No, that's I was thinking about the number of ancestors. This is the sequence of even natural numbers. So you have 2, 4, 6, 8, which is, of course, you can write as basically 2 raised to the 2 times n. That's not the same thing. I apologize. So then, of course, you can just keep going, and for example, the 48th term of this, the 24th term of this sequence would be basically a of 24. You can just keep writing it out, and you would get basically, for example, you would get a 48 there. So basically a of 24, you would get a 48 if you keep writing this sequence, and that would be basically 2 times 24. Or basically a of 23, you can write it as, which turns out to be basically 47, I suppose, 46, that's 2 times 23, right? So in fact, we see that the nth term of this, we can see that the nth term of this sequence can be written as a of n, and therefore you can write a of n is equal to 2 times n, right? The nth term can be written as 2 times n, where n is a natural number, where n is a natural number. Where n is a natural number. Similarly, in the sequence of odd natural numbers, if you consider the sequence of odd natural numbers, which is basically 1, 3, 5, 7, and so on and so forth, you can say that basically a of you can write this as basically so you can actually write this in 2 different ways. There is 2n plus 1 and 2n minus 1 if you want to. Sometimes you need the 0, sometimes you don't need the 0. But in this case, if you're starting from 1, the first one can be written as 2n minus 1. If n is equal to 1 here, if n is equal to 1, then 2n minus 1 would be equal to 2 times 1 minus 1, which gives you a 1, right? That gives you basically 2 minus 1 is equal to 1. If n is equal to 2, then 2n minus 1 will give you 2 times 2 minus 1, which is equal to 3. As you can see, we are getting the terms over here. If n is equal to 3, then 2n minus 1 is going to give you 2 times 3 minus 1, which is equal to 5. If n is equal to 4, then basically, which is this term over here, 2n minus 1 is going to give you 2 times 4 minus 1, which is equal to 7, and so on and so forth. That means that the nth term over here, a of n, can be described as 2n minus 1. there is also usually in algebra in dealing with these series and sequences and that sort of thing, you have basically 2n plus 1 as well, but that is for the case where, so for a different case, we don't have to talk about that here. But essentially this sequence of odd natural numbers can be described as, or the nth term of that can be described as 2n minus 1, right? Okay. Okay, so then basically, so here we saw that we could write this as a of n is equal to basically 2n minus 1, and there is basically some arrangements of numbers, such as, for example, which is basically, for example, this one in particular is called the Fibonacci sequence. I hope that I'm pronouncing this right, because there is many different types of pronunciations for this word. I have heard many of them, so I'm mainly confused, but I suppose Fibonacci, we can actually look that up. So it's called Fibonacci. I think he was an Italian mathematician. Well, we will get to that because my internet is okay. Italian. It's supposed to be Fibonacci. Okay. So this one is called the Fibonacci sequence. Fibonacci sequence. And this Fibonacci sequence is as follows. You have basically a 1 and another 1 and a 2 and a 3 and a 5 and an 8 and so on and so forth. And of course it's not easy to see the rule here, or how these numbers are put together, but the sequence is generated by the recurrence relation given by, so this type of relation that I'm going to write is called the recurrence relation. Recurrence relation, meaning that each term is dependent upon the other one, and so on and so forth. Meaning that a of 1, which is 1, is equal to basically a of 2, and that is equal to 1, right? Then a of 3 is equal to basically a of 1 plus a of 2. A of 1 plus a of 2, which is basically 1 plus 1 is equal to 2, right? That is a of 3. And then a of n, so these are the first 3 terms, right? And then a of n is equal to basically a of n minus 2, a of n minus 2 plus a of n minus 1, right? Which means that, for example, a of 4, which means that a of 4 is equal to a of 2 plus a of 3, which is equal to a of 4 is equal to a of 2 and 3, so 2 and 3, so 1 plus 2 is equal to 3, which is equal to a of 4. Now a of 5, for example, would be equal to a of 3 plus a of 4, which is the same thing as 2 plus 3, and that is equal to basically a of 5, which is equal to 5, and so on and so forth. So that's called the sequence is called the Fibonacci series, 1, 1, 2, 3, 5, 8, and so on and so forth. And the Fibonacci sequence, not series, I apologize, the Fibonacci sequence. Now in the sequence of primes, for example, this is an interesting one. In the sequence of primes, in the sequence of primes, which is basically 2, 3, 2 is a prime number, 3 is a prime number, 5 is a prime number, 7 is prime number, and so on and so forth, we find that there is no formula. Here there is no formula to find the nth term. Such sequence can only be described by verbal description, and so this sequence can only be described by verbal description. Now, in every sequence, we should not expect that its terms will necessarily be given by a specific formula. However, we expect a theoretical scheme or a rule for generating the terms a1, a2, a3 all the way up to a of n in succession. But, well, not necessarily is it the case that you can expect that every sequence is basically follows some specific rule. It could be, for example, like the sequence of primes, where you can actually find no rules, and that was at one time, this was actually a question of mine that I actually posted this question in a forum on the internet, that I wanted to there was something that I was doing, and for some purpose I wanted to know that whether basically the nth term of the sequence of primes can be, you can have some formula for that, which of course doesn't exist. And for the same reason, of course, there is all of these calculators on the internet that you can use. For example, if you want to check, for example, 151 is a prime number, and then, for example, then the calculator will tell you that, for example, you can see that over here, if you check 151, for example, 151 and check the number, it tells you that 151 is a proven prime, which means that there is only this way that you can check whether a number is a prime number. There is also this, there is something called the Sieve of Eratosthenes. There is also something called the Sieve of Eratosthenes. I think that's this way. Eratosthenes or something like that. Eratosthenes. So the Sieve of Eratosthenes, this is hard, I mean, there is no way to learn this word. Eratosthenes. And the Sieve of Eratosthenes is basically it's essentially a table of numbers that you can create based on some rules, meaning that first for example, you want to find out which numbers are prime numbers, for example, starting from 1 to 100 or something like that. And then you have to list all the numbers from 1 to 100, and then basically you start from the first number and then eliminate all the numbers that are multiples of the prime numbers starting from the beginning, and then at the end of once you get to the end of the table, then all that is left is basically all prime numbers. And that's, for example, one way that you can specify whether, for example, all the numbers from, for example, 1 to 100 are prime or not, and that's the only way that I know that you can do that. Otherwise, there is really no rule for that sort of thing. So long story short, there is some sequences of numbers that in which case there is no formula, and one of them is the sequence of primes, and that's that basically. Now, in the view of the above, a sequence can be regarded as a function whose domain is the set of natural numbers or some subset of it. Sometimes we use the functional notation a of n for a of n. So basically what this means is that let me read this. So basically what I just said is that, so we can say that and this is important to understand, in the view of the above, basically the sequence can be regarded as, as a function whose domain is the set of natural numbers, and or some subset of it, and so the domain of this function, meaning that the inputs of this function is the set of natural numbers, and for every input you will get a specific and distinct output, and in that view you can regard the sequence as basically as a function. And sometimes we use the functional notation a of n for basically a of n, which means that basically your input essentially becomes your index, meaning that your index is 1, 2, 3, 4, 5, 6, and so on and so forth. Here your index is 1, your index is 2, 3, and so on and so forth. And relative to that index, you're getting some output which is a of n, or a of n in functional notation. Okay? And that's basically all that we need to know so far about sequences. So now in the next video we will talk a little bit about series, and then we have a couple of exercises to do. I'll see you in the next video. Thank you.